Part 4. Same standing wave pattern with different tensions. Now we are going to do, initially what we did, we applied different tension for different number of segments. Then we applied different frequencies for same tension. Now we should work on the same number of antinodes, or you may say same standing wave pattern, but you have to change the tension and the frequency. So in this case, you have to create 3 antinodes using 150 grams of mass and see that at what frequency, having the mass of 150 grams, you get 3 antinodes. Measure the wavelength of this situation and then take the product of F into lambda. Then increase the mass. Again, adjust the frequency so that you get 3 antinodes. And at that point, measure the wavelength and take the product F lambda. For the third case, increase the mass to 350 grams. Again, adjust the frequency to get 3 antinodes, get the value of lambda and F lambda. So question 18, what can you conclude about how tension affects the wave speed? Is this consistent with what you found in the previous experiment? In the previous experiment, you remember that you had the direct relationship of frequency of velocity and tension. So in this case, what happened when tension has been increased or decreased, and also the frequency is changing. So if tension affects speed, then what happens? There's a short clip to have a better understanding what we did.
We're going to be changing the tension. Right now, the tension is established by 150 grams hanging. We're going to add another 100 grams. So now we're at 250 grams, stretching the string, a little more tension. We're looking to see if we can get the same pattern. 42, 43, 44 hertz, 43 and a half hertz, 44. Okay, now we're getting a pretty good pattern. Looks similar to what we had before. 3 antinode pattern. And then we'll look at where the second node is occurring and the pulley end. Okay, now we're going to change the tension again by increasing the mass from 250 to 350. There we go. Okay. Oh, now we're starting to see something at 56, around 57. Looks like we're getting our pattern. 57 and a half. All right, adjusting it to see where we get that pattern. We're at 58 hertz, 57.9. I think, is that right? Is that it? Okay, 57, what's your final answer? 57.9 hertz.
Okay, so coming towards the question 19, when the wave speed increases, will the wavelength need to increase, decrease, or stay the same to get the same standing wave pattern, such as the one with 3 antinodes? You see that when wave speed increases, V equals F lambda, the lambda also increases. But in this case, keeping the frequency constant. But in this case, when we have to increase or decrease the tension and the frequency, change the frequency to get the fixed 3 antinodes, then what do you think? Will it increase or decrease the wavelength by changing the wave speed? Obviously, the wave speed is changing because of the tension. but the other quantity is also changing the frequency. So what would be the wavelength? Will it be same or increase or decrease? Question 20. When the wave speed increases, will the frequency need to increase, decrease, or stay the same to get the same standing waves, such as the one with 3 antinodes? Similar to the previous question, if we do not consider the fixed antinodes, if we only consider the different tensions, then wave speed increases or decreases according to the tension, and it changes the frequency. Now, in this case, when the speed increases, do we need to change the frequency also in order to get those 3 antinodes when we increased the tension? Part 5, application. Based on your experience in this experiment, explain tuning a guitar or any other stringed instrument by changing the tension of the string. Your explanation may be based on frequency, wavelength, and speed of the wave. So you know that the frequency of a string on a musical instrument can be changed either by varying the tension or by changing the length. For example, the tension in guitar and violin strings is varied by tightening the pegs on the neck of the instrument. Once the instrument is tuned, the musicians vary the frequency by moving their fingers along the neck, thereby changing the length of the vibrating portion of the string. So you can discuss it in any manner if you are talking about the length or the frequency or the speed of the wave. So the last part, I already told that there would be some kind of questions, suggestions, and we will discuss if there is any kind of problems which may occur while performing this practical. So, first of all, I would like to add some suggestion questions. First question which can be added is how you can calculate the frequency of generator by using the values of segments, tension, and mass density. Here in this case, we had the frequency on the computer screen. We knew that. So if we have the actual frequency on the computer, but what will happen if a student is said to calculate the frequency by getting the values of the tension of the segment and the mass density? And then the second question, determine the percentage error from the actual value and the calculated value. The third question, which I suggest, is if we say the students to plot a graph between the frequency and the number of antinodes, and what kind of graph they expect from this whole procedure. And the fourth one, can they determine the speed of the wave or the tension in the string from the graphs? Some of the problems which may occur during this practical. So I think a student must be well aware of how to connect the generator with the Pasco interface with the computer system, how to operate the computer system. Then regarding the string, it should be an inextensible string, it should be uniform, and it should not hit, like it should be straight. So also the pulley which we are using, the friction of the pulley should be small, as obviously it will affect the tension in the string. If there will be higher friction, so it will be lower the tension. And while calculating the while measuring the wavelengths, I personally feel that sometimes it happens that the loops formed at the end of the vibrator and at the tip of the pulley, they are not formed very well. So it's better to measure the wavelength when there are a lot of number of segments. It's better to measure the wavelength from the central part of the thread, the central loops.